Assalamu alaikum wa rahmatullah. You are welcome to the fifth lecture in this course of probability and stochastic process. In the previous lecture, we went through some of the important probability density functions like exponential distribution, Poisson distribution, the normal distribution. We have seen several of those probability density functions, and we mentioned that this probability density function is a function which could describe the uncertainty or the randomness in the random variable or in random process. Today we continue the subject, so we will talk about two important subjects today or topics today. The first one is the mapping from distribution to another distribution. And the second topic is the expectations. How could we find the expectations or the averaging of random process or random variable? It is very, very important in applications. So today's lecture is very important lecture. So we can go through these important two topics. Let me share the online or the whiteboard so I can write. So you have already the slides there of this mapping, but I will write on the screen so it will be better for describe the topic. Okay. So now let us start with the mapping between a random variable to another random variable. If the other random variable is connected to the first one by certain mapping. Here we will talk about only like static mapping. It is not dynamic. When we talk about dynamic mapping, it means that it is like differential equation. But I will not talk about differential equations. Let us just talk about like one-to-one mapping or static mapping or deterministic mapping, like y equal to, for example, any function in x. So j of x. Let us take this case. Assume that y equal to x square. Okay. And now x is a random variable, and it has certain distribution fx of x. This is the probability density function of the random variable x. The question now that we like to answer today, in the first topic today, is what will be the distribution of y? What will be the distribution of y? So this is the question that we like to answer today. You can see the reason that we use x and y here, subscript to the parameter or the function letter f. So the reason that if we write just f, so we don't know if for what, is it for y or for x? Okay, so this is the reason that we use here y and using here x. Okay, to answer this question, it is not hard to say that, for example, assume that we have this relation. This is x and this is y, and y is function in x. So assume that we take this part, that this is the function, y is equal to j of x. So it is function in x. Okay, x is random variable and y of course will be also random variable. Okay, now if x has changed from any point, let's say x0 up to other point, let's say it is with here, sorry, I just fix this one. Okay, so we have here delta x. Okay, and here from x0 up to x1. So x1 minus x0 equal to delta x. The probability that x will change from x0 to x1, here we assume that x is continuous random variable. To change from x0 to x1 is equal to what? Equal to the area. The probability is equal to the area under the probability density function of x. So it will be integration from x0 up to x1 fx of x dx. This will be the probability that x to be greater than or equal to x0 and less than or equal to x1. Okay, now if we draw here the probability density function of x, like this one, assume that this is the probability density function of x. So this will be the area under this curve. This area representing the probability that x is moving from x0 up to x1. Okay. This, of course, x0 in y representing what? Here it represents y0. And y0 equal to the function j of x0. And x1 will be at y1, and this equal to j of x1. Okay. And the probability that y will change from y0 up to y1 must be the same as the probability of x is moving from x0 up to x1. Now let us talk about like one-to-one function. Okay, so it will be the same. So it means that when it moves from x0 to x1, it will be the same probability that y will move from y0 up to y1, because they are connected to each other like this relation. So when it moves from x0 to x1, it will be the same as movement from y0 up to y1 as probability. So now if I draw here the probability density function of y that I am looking to find, assume that it is something like that, for example, then this probability will be the same as the area under this curve. So it will be the same as the area under this curve. So it will be like integration from y0 up to y1 f of y dy. So this will be the same probability. So the same probability that x to move from x0 to x1 is the same probability for y to move from y0 to y1. Why it should be the same probability? Because they are connected by the same equation. They are connected by the same equation. Okay, now we can represent this as this way. So if delta x is very small, we can take the integration, this area when delta x is very small, it could be approximated like this one. So it is f of x delta x. Okay, this will be the area when delta x goes to 0. When delta x is very small, the integration, if you remember from numerical analysis, that it could be approximated like this one. But of course, this will be taken at x equal to x0. So the area under the probability density function of x equal to the area under the probability function of y delta y, where it is the same, that x should be taken at x0 or y will be at y0. Okay, so what we are looking for, actually we are interested to find the distribution of y, because we assume here that we know the distribution of x, but we like to know what will be the distribution of y. Okay, then if y of y equal to fx of x, here we have delta x, so it will be delta x divided by delta y. Okay. However, you should remember that the distribution, always the probability density function must be positive. The probability density function must be positive. Here, delta x and delta y, the changes of x and y, if they are not in the same direction. For example, if delta x it changed up and delta y it changed down, or the reverse, then this value will be negative. And if this value is negative, then the distribution will be negative, and this is not possible. For this reason that we can put here the absolute value. So we are interested in the absolute of the changes, the relative changes between delta x and delta y, but not in the direction, because the direction should generate negative, can generate negative, and this is not allowed. This is the reason that we take the absolute value. And of course, this could be also written as fx of x divided by the absolute value of delta y divided by delta x. It is the same, actually. I just put it like in this way. Okay. Now, when delta y goes to 0 and delta x goes to 0, this delta y divided by delta x could be approximated like dy over dx. So we can substitute this in the above equation. So in this case, fy of y equal to fx of x divided by dy over dx, and we take the absolute value in this way. Okay. However, the generated function should be function in y, not function in x, but here it is function in x. Because of that, we can simply change this one, so it becomes fx is the same, but instead of x, because we know that y equal to j of x, which means that x equal to the inverse function of y. Then instead of x, we put here j inverse of y divided by dy divided by dx, absolute value, and also we put this function to be in y, not in x. So then we can generate the distribution of y. Okay. Let us take example for that. Assume that y equal to x squared, as we said before, and we know that the distribution of x, it has fx of x. Let us keep it general, fx of x, and then after that I can put any function that we like. Okay, we know the distribution of x, like fx of x, and we are interested to know what will be the distribution of y. Okay, so we can apply the same concept that we have seen now, fy. So however, here we have simple or like small problem, that x equal to plus or minus square root of y. Actually, two different x values of x might give the same value of y. It means that assume that x equal to 5, so y equal to 25. But also, if x equal to minus 5, y will be the same, 25. Okay, so how could we handle this problem? This can be very easily handled in probability, because when we have y equal to 25, it can be because of x equal to 5, or remember, or x equal to minus 5. And they are mutually exclusive, which means that they cannot happen in the same time. X can be 5 or minus 5, but cannot be in the same time 5 and minus 5 in the same time. They are mutually exclusive events. Then we can add them. We can add them together. One at square root of y, and the other one at minus square root of y, plus or minus. So it can be at 5 or at minus 5. Okay, so let us try to find what will be the distribution of y in this case. The distribution of y in this case will be, okay, as we said before, we just apply the same equation, this equation. Okay, it will be the same as the distribution of x, but now we take what? We take j inverse of x divided by dy over dx, and we take the absolute value. Okay, what is j inverse of x? This one, because y equal to x squared, x equal to plus or minus square root of y, as it is given here. So just we apply, and what is dy over dx? Dy over dx, the differentiation equal to 2x. But remember, because we like to have the function as function in y, so instead of x, we put what is equal. So here equal to 2 plus or minus square root of y. It is a plus or minus, but here we have the absolute value. Because we have the absolute value, so we take only the plus sign. We don't take the minus sign. Okay, so this in this case will be, it will be fx of j inverse x it will be square root of y, okay, divided by dy over dx, it will be 2 square root of y, okay, a plus, because it is or, remember it is or, so since it will be plus, and it will be fx of minus square root of y, because as we said, plus or minus, as you can see, divided by, but here we don't change here, because always should be always positive, should be always positive, so it will be 2 square root of y. So in this way we can find what is the distribution of y. Okay, now you might ask, we need to see some real example. Assume that fx of x is given as exponential distribution, so it is lambda e minus lambda x, okay, and y equal to x squared. We like to derive the probability density function of y. So the probability function of y in this case, you just substitute this function here. So it will be, of course, we can take 1 divided by 2 square root of y as a common factor. So it will be 2 square root of y as a common factor. Okay. And here we have fx of square root of y. So it will be lambda, okay, times we can take also lambda actually as a common factor here. Okay, so it will be lambda here. And then we will have e minus lambda, and it will be x. So x here will be square root of y. Okay, and it will be minus or plus e. It will be minus square root. I think it will be here. It will be minus, so it will be plus lambda square root of y. Okay. However, of course, this should be concentrate. We should have concentrate here. So y cannot be it cannot go to the event. So we have to keep the total integration of fy of y to be 1, and this we will come to this issue later today. Okay, how to put the constraints that to have always the integration. Remember that the integration from minus infinity up to infinity of y, okay, of fy of y must be 1. Okay. However, if we look to this one, you can see that y must be always positive. Y must be always positive, and the distribution of x here in this case, the distribution of x is always positive. Here, this distribution is valid only for x to be greater than or equal to 0. Okay, to be greater than or equal to 0. What that means? In this case, it means that the negative sign here cannot be taken. The negative sign here cannot be taken. Why? Because x cannot be negative. X cannot be negative. X is always positive according to the exponential distribution. According to the exponential distribution, x must be positive. So since x to be negative, the probability that x equal to be negative, this part should be 0. This part should equal to 0, because the probability that x to be minus square root of y equal to 0. And because of that, this part will be removed. Why it is removed? Because we know the distribution of x, that it must be always positive. Okay, so actually what I want from you when you solve like such kind of problems, that all the time you need to discuss your solution. So what I have done here mathematically is correct 100%. Mathematically, from mathematical point of view, is correct. But if we think that x here also, this one is correct 100%, that x can be plus or minus square root of y. This is mathematically correct. But always look to the distribution of x that you use. Here in the distribution of x is always positive here. Because x is always positive, then the probability that x to be minus square root of y is equal to 0 in this case is not the same, is equal to 0. Okay, and you can easily observe that from this equation. If you look to this equation, and if you take the integration from minus infinity to infinity, this equation will go to infinity. It will not be 1. Why? Because of this part. And this part is not correct, actually. This part is not correct simply because x cannot be negative. X is always positive from the exponential distribution. From the exponential distribution, x must be positive, and this part cannot be there. Then we can omit this part, if this part equal to 0, and then our distribution, it will be lambda divided by square root 2 square root of y, e minus lambda square root of y. So this will be the distribution of y, of the function y equal to x squared. Okay, so I hope this is now clear about the conversion. However, what if f of x equal to lambda e minus lambda absolute value of x? Okay, so in this case, x can have plus or minus direction, so it will be correct for both directions. In this case, you can solve it with this equation, keeping that you take the absolute value, which means that it will be always negative. But in this case, you have two because this one plus, and this will be negative as well because we have absolute value here. So this will be like lambda divided by square root of y, e minus lambda absolute value of square root of y. Okay, so you actually don't need even to take the absolute value here because y is always positive, so it will be just square root of y. So this will be the solution in this case. So by this way, we can convert from one distribution to another distribution. So you might face such kind of problems in your research when you come to your master thesis or your PhD thesis in the future, inshallah. So you can find that you know the distribution of x, and x is, for example, Gaussian distribution. But in your channel, for example, you find that y is some function in x, and you need to know the distribution of x in order to find, for example, the probability density function of y. So you can find the probability that y to be between certain values, or what is the probability of error, and so on. So this is one that we can face in research. Okay, so this is the conversion or the mapping between different like mapping. We have also the slides, if I remember, there is also the case if you have multiple values, if you have, sorry. Me. Okay, so maybe you can see here that we have this, we gave here some examples about this. So, and also we gave the case if you have function in multiple random variables like x1, x2 up to xn, how to handle them, okay, by using Jacobian matrix. But we will come later to this, as I mentioned before. We come later to more equations like that. In this slide, we saw, or we present the Rayleigh distribution or Rayleigh distribution, and we know this Rayleigh distribution. If you talk digital communication course and propagation, we know that this Rayleigh distribution is one of the channel modulus of the received signal magnitude. So the received signal magnitude, due to the multipaths, it will be received random, and it will be it could be represented as a Rayleigh distribution. Okay, and actually Rayleigh distribution is nothing but just two exponential distributions, as you can see, and two normal distributions with zero mean and unit variance, or it can be actually variance sigma square, and then it will be x1 square plus x2 square. So you can generate two random variables like x1 and x2 square, and then you take the square root of this. Y will be, in this case, will be a Rayleigh distribution, and it can be derived, but we are not here that derive them, or this is not important to derive them here in this course. but it is important to know the characteristics of Rayleigh distribution. So Rayleigh distribution, it has this shape. And this is the shape of Rayleigh distribution, f of x equal to x. You can see that Rayleigh distribution is based only on one parameter, which is sigma. And this sigma actually is sigma squared is the variance of the normal distribution, which formulated this Rayleigh distribution. Okay, so it is given as sigma squared. And it is called the Rayleigh parameter. So Rayleigh parameter depends on only single parameter, which is sigma. Normal distribution depends on two parameters, if you remember, the mean, mu, and sigma, which is standard deviation or sigma square, is the variance. However, in Rayleigh distribution depends only on single parameter given as sigma or sigma square. And to compute the commutative distribution function, we can take the integration as we can see here from 0 up to a for x of x, and this will be like 1 minus e of or exponent of minus a squared divided by 2 sigma squared. If you go back here, you can see here y is always positive as well. Y is always positive, as you can see. So it is not, it cannot be negative because it's equal to x1 squared plus x2 squared. x1 and x2 are both independent. They are independent normal distribution or Gaussian distributions. Okay, and both of them, remember, both of them must have zero mean, but it can have any variance sigma squared. Okay, if they don't have zero mean, then if they have some specific mean, in that case, we have Rayleigh distribution or Rice distribution. Actually, this represents in wireless channel, if you have rich multipath propagation without line of sight, there is no main path, there is no strong path, but all paths they on the average they are the same on the average within certain scattering value. This could be represented as Rayleigh distribution. In case that you have single strong path, or sometimes it is mentioned as line of sight path, and you have many other multi-paths, then we have Rayleigh distribution or Rice distribution of the received signal. Okay, so this should be remembered. This is the connection between the Rayleigh distribution and wireless communication. So this will be the distribution of Rayleigh, okay, and this will be the CDF of the Rayleigh distribution. Then we have the chi-square distribution. Before I go to the chi-square distribution, let us go to Octave or MATLAB to make simple calculations about this normal distribution and Rayleigh distribution. Okay, I will stop sharing here. Okay. Maybe this time we go to MATLAB. By the way, it is the same exactly. I mean, at least the functions that I am using in this course, they can be run as they are in MATLAB. So there's no difference between MATLAB and Octave, at least based on the codes that I am using here in this course. Okay. Okay. Let me share this one. Take some time for MATLAB to come. Yes. Yes. So now you can see here in the MATLAB code, and okay. First we can generate our maybe if I want now to generate right distribution, of course there are some ready function in MATLAB and in Octave to generate right distribution, but I like now to generate them based on the Gaussian distribution. So we can generate a Gaussian distribution in this way. So x equal to let's say that the sigma equal to let's say 2. Okay, this will be sigma times in this case the variance will be 4, because the number that you multiply in random will be sigma, not square, and the variance you take the square for this one. So times random n. When you add n, as you know, that it becomes Gaussian distribution or normal distribution, and then you put the number of rows. I will put 2 rows because I want to generate 2 functions, okay, or two series of numbers, and I will put like 1000 element. Okay, so in this case, because it is 0 mean, so now I have if I write for example size of x, you can see it is 2 rows and 1000 column. Okay, and it contains a random number. If you want to plot this random number, simply you can say like plot, for example, x. I will draw one of them. Okay, only one of them, and this case. So you can see here that yes, maybe you cannot see the draw here. Maybe it is better to share the screen, not MATLAB, that so you can see everything on the screen. Just a minute. Stop. Use screen 2. Yes. Now you can see everything on the screen. So this is the what is generated now. This is the random number. This random number fluctuating. You can see that it has positive and negative values, because normal distribution can be positive and negative. Okay. So now I will make it off this one. I assume that you want to generate a line distribution with sigma equal to 2. So simply that you will make it like y equal to, I will take the square root, okay, of x1 square. So I take x and the first element of x, all elements in x1, make the dot square root of 2 of double. I take the square of this number. I took this dot. Actually, this dot means that element by element. Without this dot, you will receive error message, because vector cannot be squared. Okay, so when you put this dot, it means that you square it element by element inside this vector. Okay, plus I take the second element now, that it is number 2, and all 1000 random number samples, and again I take square. And I take the square root for everything here. Of course, you can write square root, or you can just make it in this way, that it is 0.5. Okay, with the power of 0.5, or you can write square root. Okay, now I generate y. This y now is Rayleigh distribution. Y here is Rayleigh distribution. I can for example, if I plot y to see how y will looks like, this is y. I will bring it to this so you can see it. Now this is y. You can see that this y now is positive. It cannot be negative. From 0, it can take any value from 0 up to infinity. Okay, and okay, yeah. So what else? If we are interested to know what is the probability that y to be greater than 2, for example, or because it is a Rayleigh distribution, assume that your channel will work if the received magnitude of the signal is greater than 2. What is the probability that x to or y to be less than 2? So we can do it very easily as we showed before. So I can take the length of the vector of find y less than or equal to 2. Okay, so now this will give you the length of these elements out of 1000. So I will write here NE equal to this value. So now if we check this, it gives you 431 sample y was less than or equal to 2. Okay, what is the probability in this case? The probability simply by the long run case that it will be NE divided by the total number of samples. So we have here 1000 samples. So it will be, the probability is 0.4310. So you can see how much easy that to make the probability or to compute the probability with Monte Carlo simulation. You generate the numbers and you compute the numbers where this event that you are interested in achieved, and then divide them by the total numbers of the samples that you have. But you need to remember to provide enough number of samples. But it is much easier now if you want to make it with the calculations. Of course, in case of Rayleigh distribution, it is easy to compute the probability that y less than or equal to 2. You have already the formula that we showed now in the last slide that we showed, but we have some distributions which can be very complicated, very complicated to solve the probability density function and to find the integration from certain probabilities. But here it becomes very easy. Okay, here it becomes very easy to find the these values. Okay. If you want to check how should be the distribution of y, or what is the shape of distribution of y, in Octave and MATLAB you can use histogram. So if you write histogram that of y, okay, and then you can divide the number of like bars or the number of samples in each one. So you can see, I can bring it here so you can see it. So this will be the histogram. So but it is not normalized here. So the histogram gives you how will be the distribution, or the distribution of those numbers. So it follow this Rayleigh distribution. If you increase it a little bit, so if for example, if we put histogram but we put 100 instead of 50, so you can see, sorry. Yes, you can see here. So it becomes more samples. So it covers somehow the Rayleigh distribution. I can keep this one, and also I can draw over it, for example, the histogram of x of 1 and the other samples. Okay, so okay, so now you can see how will be the distribution of the histogram of x. So you can see that it follows the Gaussian distribution. You can see the 0 in the middle here, as you can see that we have 0 in the middle, and then we have the other tails. Of course, as you increase the number of samples, more than 1000, you can be more accurate that distribution of the number that you are or the probability function represents. Okay. Yes. So let us now, if we go back to the slides to see what is next here, we have here, as you can see, the I can just, yeah. So you can see the chi-square distribution. Actually, we have many distributions are based on normal distribution. And from the previous lecture, we talk about the central limit theorem and why Gaussian distribution or normal distribution is the most important distribution in case of continuous random variables. So many other distributions actually they are just different forms of the Gaussian distribution. For example, this chi-square, which is widely used in many applications, like especially, for example, to measure what is known as confidence interval, also to check the confidence of certain hidden random variable within other random variables. We will see some applications later about chi-square distributions, and it is given by this formula as you can see it. So it is actually nothing but the summation of xi square. Xi is a just Gaussian distribution with zero mean, as you can see here. So it is Gaussian distribution with zero mean, and you take the square of every one of them, then you take the summation n times. You take the summation n times, then you will have chi-square distribution with like it is called that n is the degree of freedom. N is the degree of freedom, and in this case we have the probability density function is given by this formula that you can see in front of you here. So this is the formula of the probability density function of y. It is a little bit complicated, this formula. However, with the Gaussian or with the Monte Carlo simulation, it is very straightforward to find any value or any probability or any computations needed based on this formula. For example, what is the mean, what is the variance, what is the probability to be within certain values, what is the moment generating function of this, as we will see later. So a lot of applications we can use with Monte Carlo simulation. And here gamma is called gamma function. And gamma function actually, if you have real number or if you have integer, it is the factorial. But this gamma function for general for any value, and it is given by this formula. Okay. Before I continue, I will go back again to MATLAB to see how could we, for example, make. Sorry for this. Yes. Come on. Yeah. So let us now. We like to build like Rayleigh distribution or generate a random variable with the Rayleigh distribution, but it has, let's say, 4 degree of freedom. Okay, 4 degree of freedom. So what I can do here, I can simply write that, for example, clear all. So I will clear everything. So all. Okay, so now everything is cleared, and I will generate 4 random distribution, normal distribution with zero mean and any sigma. Okay, this time let us keep sigma equal to 1. Okay, so it is random normal. Okay, and I will generate 4 elements because it has 4 degree of freedom, and I will generate 10,000 elements. So let me do it in this way. So to be more professional way, that n equal to 10,000. Okay, and then I will generate x equal to random n with 4 elements and n. Okay, so now we have generated x random variable is nothing but it is a vector matrix with 4 rows. It has 4 rows, and then it has n column. N equal to 10,000 column. Okay, so if, for example, just I will show you like the first 4 by 5. So I will print x from all rows. I will print only the first five columns. Okay, so now you can see this is the matrix that if I take the first 5 elements. Okay, so you have 4 rows and 5 and actually 10,000 element, but I printed only the first 5 elements. Okay, now you want to generate for some application that you know that you are now in the beginning of this your master study. So in the future you will have several courses. You might meet some course that you need to, for example, in reliability course, if you have one course in reliability, for example, or in some applications, physical applications in optics and so on, and you need to generate now Rayleigh or chi-square distribution with a number of freedom equal to 4. So simply you can do it in this way. So I have y equal to, okay, of course I can take the sum directly. For example, I show you, if you take the size of sum of x, okay, so it will give you 1 by 10,000. What it means, when you take this sum, they will add all the normal distributions that we have. We have 10,000 elements. They will sum them together. Okay, they will sum them together like row by row. Then you will have one column, one vector with 10,000 elements which have the summation. What will be the distribution here? The distribution here is still normal distribution, because the summation of normal distributions gives you normal distribution. I repeat, the summation of Gaussian or normal distributions, it will give you the same Gaussian or normal distribution. This is fact. Okay, so here we will still have normal distribution, but y actually equal to the summation of x but square. Everyone should be squared first. So y equal to the same as I did now, sum of what? Of x, but every x must be squared. Every x must be squared first. Okay, so in this case, I will have Rayleigh distribution in this case, and here y is Rayleigh distribution with like degree of freedom equal to 4 and with sigma equal to 1. The same y actually you can generate it in this way. The same y you can do it in the conventional way, that x of, I take the first element, all vectors, and then I take square plus the second one, x of the second one and all elements, and then I take square for each element, a plus, and so on up to the fourth element. It is possible to do it, but just think that if you want to generate this chi-square, but with degree of freedom equal to 10 or 12, it is not, I mean, practical to do it in this way. Much easier to do it in that way, that you take just the sum and you take the square of every vector there. Okay, now if you want to, if I asked you what is the probability that this Rayleigh distribution to be less than or equal to 5, it will be very simple in this case. So NE, the number of elements to be less than 5, I will call it NE. You can call it with whatever you like, and equal to find length of the vector of find. I am looking for the instances that y I want it to be like, for example, less than or equal to 5, less than or equal to 5. Okay, and then this gives you the number of events. NE. Yes. So this will be happen 7,237. So the probability will be NE divided by the total number of samples, and this is the probability. So the probability that this chi-square with number of freedom equal to 4, the value to be less than 5 is equal to 72%. And now if you go to the slides and you solve that complicated equation and you make the integration of from 0 up to 5 to find this solution, you will get a very close number to this one. But of course, that one is analytical solution, and this one, we call it Monte Carlo simulation. Monte Carlo simulation is different, by the way, than numerical solution of integration. A numerical solution of integration is something is related to like numerical analysis. It is deterministic process. But here we generate random numbers and we check when this happened. Okay, so there's big difference between these two issues. Okay, let us open the slide again to see. Yes, this is the chi-square distribution. As I said, we have Rice distribution or ratio distribution, sometimes they called. And in this Rice distribution, actually, it is exactly the same as a Rayleigh distribution, Rice distribution, but in this case, we have non-zero mean of the normal distribution. It is non-zero mean. Okay, and also we have Nakagami M distribution, which is widely used also in channels. which also could be like, it can represent actually from Rayleigh to Raytian to the additive white noise channel, and we might have time to come to it later. Okay, but before I go from this, I return back to this MATLAB or to this Monte Carlo simulation, and now I asked you to generate a Rice distribution or Raytian distribution. Okay, I will clear everything, clear all. Okay, so Raytian distribution, simply I will generate the two dependent normal distribution. I will use, for example, sigma equal to 4 times random n element and two rows, and for example 10,000 samples. Okay, the difference now that I will add some mean for the values. So X has now some mean. Okay, so of course the mean should be actually orthogonal for each row, but for simplicity here, just I will add the same mean. So the mean can be, for example, 2. Okay, so now we have mean. After adding the mean, actually, and now y equal to the square root of x of 1, the first element, and you can take, of course, the sum as we showed before, but just for simplicity here, or for the explanation, 1 of all elements square plus x of the second one and all elements square. Again, remember that you can make the sum, the sum, which is can be easier. So this will be the result. So the result is now Raytian distribution. The result has now Raytian distribution. If I draw the histogram of y, so it is somewhere here. I should show it. So this will be the distribution of the Raytian or Rice distribution. And now you can also calculate the probability. You can calculate the probability to be within certain values. You can compute the CDF value. You can, all elements related to this uncertainty or the random process can be easily generated with this Monte Carlo simulation. Okay. Okay, let us take this. Okay. In this example, I wanted to explain to you how could you make your own probability density function. How can you generate your own probability density function? Sometimes you have certain problem that you want to express its uncertainty. Okay. By the way, it is not always easy to do that, but with the practicing, if you start to do it with many ideas, or you try to find the probability density function for certain problems that you face in physics or in electrical engineering and communication, try yourself to derive the probability density function. After practicing, it becomes easier and easier with time. Okay, the idea here that we assume that we have this circle, and this circle has radius r capital. Okay, and you drop your pencil, the head of your pencil, somewhere in this circle. Okay, so the question that what is the probability density function of the location of this drop that you make within this circle? What is the probability density function of that of this drop? Okay, so maybe I go to the after this we will take a break. Okay, so just let me go to this whiteboard, so to write it on the whiteboard. Yes. When you have the right screen and normal screen, the mouse becomes problem here to how to control the mouse. It is not easy, but this second screen actually doesn't have the capability to write on it. So I need to reshare. Yes. So now you can see here. So the idea that you have circle, you draw some circle, and this circle, it has radius r, okay? And now you want to build the probability density function of a point randomly dropped there. So if you put the point here or here or here or here, anywhere in this circle. So what is the probability distribution of this line? Okay. You might think that this example, it doesn't have application, but no, it has many applications. One example is to what is the distribution or what is the probability function of a mobile moving in certain like cellular, like one cell, for example, in mobile network. Okay, so if we have one cell, circular cell in mobile network, and we want to know, of course, mobiles, people like carry mobiles can be anywhere in this cell. Okay, now we like to build some probability density function representing the location of this random mobile, which can be uniformly distributed anywhere in this circle. Okay, so if you have been asked this question, how could you find the probability density function of that mobile if it is uniformly distributed within this circle? Okay. The location of every mobile, actually, it can be represented with two issues. First is, for example, assume this is the mobile. So first thing is the length of the mobile from the center of the circle. So I call it like r small. So this r actually is a random number. Okay, this r is a random number. Okay, what else? R is not enough because r, this user also has the same r, or this one, or this one. All of them, they have the same r. The second thing that we need to know is the angle with the x-axis theta. So we need to know r and theta. Once we know r and theta, actually we allocate the point precisely. Okay, but this point actually is normal. We don't have any information where this point will be. So we like to build the probability density function of this point. Okay, the first thing, assume that the mobile is dropped at distance r from the circle. Now, if we take circle here, okay, what is the probability? What is the probability that now we can compute the CDF? The CDF says that the probability that the random r, the random number r, to be less than or equal to some row. Row is any element. You can call it x0, r0, anything. Okay. So what is the probability r to be less than or equal to row? What is the meaning of row? Row is this, for example, if we assume this is row, what is the probability that you will have your mobile inside this smaller circle, okay, instead of the bigger circle? This probability, actually, if the mobiles are uniformly distributed anywhere, will be the area of this small circle divided by the area of the bigger circle. So it will be the area of the small circle will be by rho square divided by the area of the bigger circle will be by r square. So by cancelled by, so the CDF equal to rho square divided by r square. But we know that the distribution of r is equal to the differentiation with respect to rho of the CDF of rho. This is the CDF actually. CDF is the probability r less than or equal to rho at rho equal to r. So now you need to differentiate this equation. So the differentiation equal to 2 rho divided by r squared at rho equal to r, and then equal to 2r divided by r capital. So the probability density function of r is simply 2r divided by r squared. So this will be r squared. Okay, so this is the distribution of r. What is the distribution of theta? Actually, theta can be any angle from 0 up to 2 pi. From 0 up to 2 pi. So theta will be uniformly distributed, uniformly greater than or equal to 0, and this than 1 over 2 pi. And this will be the distribution of theta. It can be from minus pi to pi, or from 0 up to 2 pi. It is up to you. So from 0 up to 2 pi, and the magnitude will be 1 divided by 2 pi. So this is the way that we can generate the probability density function of this problem. I can give you, but I will not solve it now because of the time. If you have same lines like this, it is well known problem. Okay, and now if you drop small sticks here, and the stick, if the length here is, for example, L, or maybe we call it X, the length, the difference between those lines is X. And now you draw, or you drop a small stick with length L. And L is less than X. Okay, L is less than X. What is the probability that this stick will cross those lines? What is the probability? What is the probability that the stick will come exactly between two lines, or it will cross the two lines? It is very similar to the problem that we solved today, but it is very interesting because with this Monte Carlo simulation, you can also divide determine the value of pi without making any measurements. Anyhow, we might come to this later, maybe not today, but maybe other day that we can solve it when we have time. But now let us stop at this slide and to have break for 15 minutes. After the break, inshallah, we will come to the expectations. The expectations is very, very important topic in the probability theory. The expectations, when you have the expectations, you move or you convert your problem from uncertainty, from probability word to math, to conventional math world, as we will see after the break. But if you have questions before we take the break, please, you can ask. Or you can prepare your questions. Also, you can send them using your chat. You can drop your questions. But now we take a break, inshallah, for 15 minutes. So it means that now it is 11:20 up to 11:35, inshallah. Is it okay? Inshallah. 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 We continue and we start with the expectations in this second part of today's lecture. And again, let us start with the whiteboard. Yes. Okay. Yeah. So what is the expectation? And what is the rule of expectations, or the applications of expectations when we talk about expectations in probability theory and in general, in stochastic process as well. So let us start with very simple example, and we will extend this example to be in general discussion. Assume that we have a class with, let's say, maybe 8 or 10 students, and the final grade of those students, assume that the grade is out of 5. So it's, here in Finland, we have the grading system based from 0, which means fail, then 1, 2, up to 5. So this is the grading system. 5 is the best grade, the highest grade, and 0 means fail. Okay, and assume that we have the same grading system for 8 students, and those students have this grading that we have is given by, so for example, we have 1 student get 0 in this course. We have 8 students. and one student, he got 1. We have 2 students get 2, 2, 2, okay? And we have also 2 students get 4, okay, 4 and 4. So now we have 1, 2, 3, 4, 5, 6. And then we have, let's say, 1 student maybe got, or 2 students get 5. Okay, so this was the distribution of the grading system of in that class. So we have the number of students is 8. Okay, so we have 1 student get 0, and 1 student get 1, 2 students get 4, 2 students get 4 and 2 and 5. Okay. If I asked you now, if in the beginning, if we don't know the how, or the students how they which one get this grade, so only teacher knows, but the others they don't know. If I asked you, 1 student had been selected randomly, and I asked you what is the probability that this student received grade 0. Okay, so now you don't have any previous information about the students. Okay, so in that case, it will be assumed as equally likely. Okay, so the probability that x equal to 0 for this student is simply will be 1 divided by 8. Why? Because we have 8 cases and we have only 1 student received grade 0. So the probability that this student is the one who received 0 is equal to 1 divided by 8. If I asked you, what is the probability that this student receive grade 2? In this case, how many students get 2? So they are 2. So the probability, it will be 2 divided by 8. So it will be 1/4. And so on. So by this way, you can find the probability for each grade. Okay? If I ask you another question, that I want you to calculate the average of the grades. The average of the grades. So the average number of the grades, if I call them, for example, J bar, the average will be, as we know about the average, we take the summation, we divide by the number. So it will be 0 plus 1 plus 2 plus 2 plus 4 plus 4 plus 5 plus 5 divided by 8. So this will be the average. So the average here will be 5 plus 5 is 10, 4 plus 4 is 8, plus 2 is 10, 10 plus 10 is 20. It will be 23 divided by 8. So the average will be 23 divided by 8. Okay? So this will be the average of those students or for this class. That's fine. This number, actually, if you look to this number, this one, it could be like decomposed in this way. So I can, in the same number here, I can say that it is 0, this 0, times 1/8, because every number here divided by 8 plus 1, the grade 1, also multiplied by 1 divided by 8. And we have 2 here, 2 multiplied by 2 by 8, because we have 2 students get 8. Okay, plus the grade 4 multiplied by how many students get 4 is 2 students. So it will be 2 by 8 plus 5 times 2 by 8. Okay, so actually finding the average is nothing but multiplying the parameter by its chance to occur. So 0 is multiplied by its probability, and 1 multiplied by its likelihood or probability. 2 also multiplied by its probability, and so on. So actually, this will give you exactly the same result, 23 divided by 8. So this actually is represented as, so that the average is nothing but the summation of xi for each one multiplied by the probability that x equal to xi, and from I equal to 1 up to n is the number of the parameters that you have. So this actually a general that I started with this simple example, but it retrieved the general concept of averaging. Averaging is nothing but multiplying the parameter, the random parameter, by its probability in case of discrete random variable. So by this way, you can compute the average for any random process. I give you example. Assume that that you have a discrete signal generator, and this signal generator, it gives you, let's say, probability. It gives you 3 values. It can be, for example, -2 volt, 0 volt, and 2 volt. And the probability that x equal to -2, assume that it is 0.1. The probability that x equal to 0 is equal to, let's say it is 0.5, and probability that x equal to 2 volt is equal to the rest. The rest, of course, will be 0.4 because the total must be 1. Okay, so now we have this random generator gives us these values from -2 to 0 to 1. And I asked you what is the average, what is the DC value of this random voltage generator. So this random voltage generator, it can be between -2 or 0 or +2. So it has, sometimes it can be at -2, it can like 0, it can be 2, it can be 0, it can be very small like -2, 0, and so on. So something like that. A random signal generator. What will be the mean? Very easy, that the mean, the average of x will be, we apply this formula. The event multiplied its probability. The event multiplied its probability. So the event here, -2, what is the probability that the signal to be -2 is 0.1. So it will be multiplied 0.1 plus the signal to be 0, 0, multiplied by its probability is 0.5, plus the signal is 2, its probability is 0.4. So it will be 2 times 0.4 is 0.8, 0.8 minus 0.2 is equal to 0.6. So the average here, or the DC value of this random signal, is 0.6 volt. It is simply like that. So the averaging, that to take the average of any random signal, is that the event in the discrete case is the event multiplied its probability of occurrence. Okay, and what if this signal is continuous? It is exactly the same. Nothing. It is not as expected. So the average will be, if x is continuous, it will be x times it is the probability. Of course, it is probability is the probability density function fx of x dx, and then we take over all possible, like the available, like domain from -infinity up to infinity. This gives you x hat or x bar, or the average of x. Usually we use mu x. Okay, so this is in the case of continuous case. If I asked you what is the average of the exponential distribution, and fx of x of the conventional distribution or exponential distribution is lambda e minus lambda x, and I asked you what is the average of this one. Okay, the average mu x will be the same as we said. So integration x here is greater than 0, so it becomes from 0 up to infinity. Okay, and then lambda is not functioning x, so we can't take lambda outside the integration. Then we will have x times e minus lambda x dx. This will be the average. And now we can compute the average, because here we have x times e to the minus x. We can make the integration by parts. so it will be lambda. Okay, so we keep x as it is, x here, and we take the integration of e minus lambda x will be minus lambda x divided by minus lambda. So we can take the minus sign here, lambda, and it will be plus the integration. We integrated this first, so it will be 1 over lambda. Again, of course, here lambda is multiplied in all this function, and this will be e minus lambda x, and the differentiation of x equal to 1 dx. This is the integration by parts, and again, we take this integration, e minus lambda x, it will be the same, so it will be here minus lambda times x, e minus lambda x divided by lambda plus 1. Oh, sorry, this will becomes minus because here we have minus. Okay, I just make this minus 1 divided by lambda square e minus lambda x, and the integration limit is from 0 up to infinity. Okay, so now if you divide, if you use infinity, when you use infinity, e to the power minus infinity is 0, e to the power minus infinity is 0, x of infinity is equal to infinity, but actually the declines or the decreasing in e minus lambda x much larger than x, so this will be 0. So if when you take to infinity, the result will be 0, and 0 minus minus, this will be plus lambda, and you multiply with 0, so 0, this will be 0, and this will be e of the power minus, it will be also 1, so it will be 1 divided by lambda square, and this will be 1 divided by lambda. So that the average of this will be 1 divided by lambda. This is the exponential for the exponential distribution. So the idea is that one. So taking the expectation, sorry. Yes. Can you see still the whiteboard?
Yeah, we see it.
Yes, okay, good. So now the expectation in general, that we can say that the expectation, we use this term, expectation of any of x, for example, is equal to, in the discrete case, summation xi, probability that x equal to xi, in case of mass, probability mass function for all i, available I, and in continuous case, expectation of x is equal to the integration x fx of x dx from minus infinity up to infinity. This is in general. Now we can extend this expectation actually not only for x, but for any function in x. What that means? Means that the expectation of j of x for any function is exactly the same. For example, in case of discrete probabilities or discrete random variables, will be summation for all I, then it will be j of xi times probability that x equal to xi. We will see some examples about this. And also for the continuous case, it will be integration from minus infinity up to infinity, j of x times fx of x dx. Okay, so this is in general that you can use the expectation to find the averaging of j of x over x. What that mean? If we come back to the example of the norm of the discrete voltage, that the voltage it has -2, the probability that the voltage equal to -2, we said that 0.1, probability that the voltage equal to 0 is equal to 0.5, and the probability that voltage equal to 2 volt is equal to 0.4. The previous example. Now we computed the average. So the averaging of this voltage, the expected value of V or the mu V is equal to, we said that it will be -2 times 0.1 is minus 0.2 plus 0 plus 0.8, and we said that the average will be 0.6 volt. Okay. Now if I ask you what is the total power in this signal, what is the average power in this signal? So the average power actually is function in V. So the average power is equal to expectation of V squared. Of course, you can divide by R, but assume that here that is the resistance equal to 1 ohm. Okay, for simplicity. So the expectation of V squared, it will be what? It is the same as we show here. The function multiplying its probability. So the function here will be v squared. Okay, here minus 2. Minus 2 squared is equal to 4 times its probability is 0.1 plus 0 squared is 0 times the probability is 0.5 plus 2 squared is another 4 times probability is 0.4. So here we'll have 0.4 plus 4 times 0.4 is 1.6, and the result will be 2 watts. Okay, so it will be 2 watts to have the average power of this random signal generator. Okay, and if I asked you what is the average power in the AC part in this signal, so this signal, this is the total power, DC plus AC. The expectation of V square is the total average power in this signal. But if you are interested in the average power in the AC part only, not in the total signal, so this will be the expectation of what? Of V minus, we subtract what? We subtract the mean, the DC value, and then we take the square. We take the signal, we subtract from it, it is DC value. Then what is left? What is left is only the AC part. So this gives you the average power in the AC part, which is nothing but the variance of any random variable. So the variance of any random variable, expected value of x minus mu x square. This is known as the variance of any random variable, which means that the power, from electrical engineering point of view, it is the power content in the AC part, not in the DC, in the AC part. So this is the meaning in electrical engineering. Okay, so now we can compute this easily. So to compute this, the expected value of V minus the mean of the voltage square. Actually, we can expand this one. So it will be expected value of, it will be V square minus 2V mu V plus mu V square. Okay. The expectation is linear operation. What that means? The expected value of any alpha times x, alpha is a deterministic number, okay? It is a scalar number, plus beta y plus gamma, where alpha, beta, and gamma are all scalars or any numbers, okay? And x and y are the random variables. You can expand this, you can take it alpha, you can, because this is deterministic number, so you can take it outside the expectation. Expected value of x plus beta, expected value of y plus alpha. Because the expected value of any real number, for example, expected value of y is equal to 5. It's simply like that. Okay, so it is linear operation. The expectation is linear operation. We apply this concept here. So what we get here expected value of V square minus 2 mu V, because mu V now is the deterministic number. Mu V is the average. We have already taken the expected value of V times expected value of V plus mu V squared is also a deterministic number. So we take it out from the expectation. Okay, the expected value of V is nothing but mu V. So mu V times mu V is mu V squared. And here we have minus 2 mu V squared plus mu V squared. This will be mu minus mu V squared. So it means that the variance of the voltage square equal to the expected value of V squared minus mu V squared, which actually very intuitive, and there is sense here, because it means that the power in the AC value, equal to the total power minus the power in DC value. Okay, from electrical engineering point of view. So now, but this is, by the way, this is generally true. I mean, you can always say for any random variable, sigma x squared equal to the expected value of x squared minus mu x squared. This is generally true. Okay, now we apply this to the previous example here. We know that mu v equal to 0.6, okay, and the expected value of v squared equal to 2 what? Then what we can do here is this will be, as we said, 2 minus 0.6 squared, and this will be 2 minus 0.36, and this will be 1.64 or something like that. What? Okay, now we can compute the average power contains in the AC part. Okay, so this is very important because variance is very important parameter to be computed, because it gives us how scattered or how the numbers are distributed around the mean. I give you another example to explain this this meaning. Let us go back to the same example of the grading of the students. Okay, we showed that before that we have the students grading was let's say it was 0, we said 1, 2, 2, we said 4, 4, and we said 5 and 5. Of course, here the probability that the grade equal to 3 is equal to 0 because we don't have grade 3 here. Okay, and we said that the average of this one was 23, we said divided by 8. So if we want to compute this exactly, how much it will be, if I use my calculator now to give, sorry, divided by 8, so it gives 2.87. So the grade is 2.87. Okay, this is the average grade. Okay, and now if you got only the average grade of the students, but this might not indicate how was the distribution of those grades in the class. For example, if all students they receive the same grade 2.87, if we assume that it is possible to have 2.87 as an grade, so if all students get 2.87, 2.87, and so on up to 8 students, they everyone gets 2.87, then still we will have the average equal to 2.87. Or maybe we have another distribution of the grade. So assume that the students was like 0, 0, 0, and some students they get 5, and maybe one student get to 3 or something like that. So the average is still 2.87. So the average gives you some indication about the numbers, but it will not give you how was the variance or how was the scattering of these numbers around the mean. How could we evaluate this value? By using variance, because variance, it says that what is the variance? Variance sigma of x squared equal to the expected value, the average of what? Of those numbers, the random numbers, minus the mean, all square. So this gives us some indication about how scattering the numbers around the mean. For example, if this number is large, means that the actual numbers are scattered too much about the mean. But if this number is small, it means that the random numbers are very close to the mean. If sigma equal to 0, if sigma x equal to 0, it simply means that all numbers equal the mean. There is no randomness here. So actually, the value of the randomness, or the quantity of the randomness, or how much randomness we have in the data, is expressed by the variance. As higher variance we have, as higher randomness we have in the random variable. As lower variance we have, it means that lower randomness in the random variable. Okay, so this is in random variable. The measure of the randomness in random variable is given by the variance. The measure of randomness in random process is it is given by the correlation. But we will come later when we talk about random processes later, or stochastic process. We will talk more about how to measure the randomness in the signal, how to measure the fluctuations of the signal, and why the correlation is related to the power spectral density. What is the relation between bandwidth and the bandwidth of the signal and the randomness of the signal, which is evaluated by the correlation function. But when we talk about random process or random variable, we talk about variances here. So the variance is a measure to give you the how much the signal is randomized around the mean. For example, if we have this shooting game, okay, this shooting game, okay, and then one of the shooter that they got this this shooting points, for example. Okay. So actually, this guy, it seems that he's like me, so he didn't know how to shoot, and then the randomness of his shooting is very widely distributed or very much scattered. Okay, maybe if you take the average of this guy, the average of xi, maybe it gives you some x star and x star something maybe here. Okay, so maybe the average is here. But does that mean that this shooter is good in shooting? No, because the randomness is very large. Even the average is very close to the mean or to the target. The average is very close to the target, but still the randomness in his shooting is very high. So the conclusion that this guy doesn't know how to shoot. Okay, now let us take another guy that he was shooting in different way. So let us have the same experiment. Okay, and this guy, his shooting was, let's say, this way. Okay, now if you take the average of this guy, maybe you will get something here. Okay, this is the average. Oh, sorry. This is the average now of this guy. Okay, this guy has less randomness in shooting than the previous one, because the variance here, for example, let us assume that this is the variance of first guy. This is the variance of second guy. It is clear that the variance of second guy is less than the variance of the first guy. Okay, so he has less randomness in his shooting, but the average of this guy, mu x1, is closer to the target than the average of this guy. So in estimation theory, we say that this estimator, it has this variance or less randomness, but higher biased. So it is biased from the target. So actually, this guy is easier because what he need little training. This guy, he need little training just to move his shooting to this direction. So this guy, even the mean is larger than or like more far the target, but it is easier to train this guy than the other one because he has less randomness in his shooting. The variance of his shooting is closer. What he has the problem of just variance, just biased. So since we need to add some, so we can teach him or her little bit how to move his shooting in order to be closer to the target. But this one actually, for sure that it is much more difficult to train this guy to be good shooter because his shooting is mainly random. Okay, so now we can see that what is the meaning of variance. Variance means that you are closer to the mean, that regardless if the mean is close to the target or not. But variance means that you are closer to the mean, and this could be measured by the variance factor, which is given by sigma x square. And sigma x square, I repeat, is mathematically computed by this formula that sigma x squared equal to the expected value of random variable x minus the mean of that x all square. So this is very general, very important equation that we will face it many times in this course. And if you take the square root of sigma x squared, so we have sigma x, and this is called the standard deviation. This is called variance. This is the variance. And this is called the standard deviation. Standard deviation. Okay. Okay. So this is actually the important thing that we need to all the time to know about the expected value. So the expected value, when you take the expectation for any function in any random variable or random process, the result is not random anymore. The result is just mathematical equation. The result is deterministic. When you take E expected value, then it means that you convert from random word to deterministic word. Okay, so when you say that expected value of X, then we have the mean. The mean is something deterministic. Okay, when we say expected value of X squared, we take the mean of the square values, which is in electrical engineering means that the average of the total power. Okay, and the average of the total power is deterministic, is not anymore random. X is random, X squared is random. When you take expectation, it is not random anymore. It becomes deterministic. This should be, you should remember this very well. Okay. Now assume that, for example, you know that, of course, it is not allowed, but assume that there is some game, and in this game that you send message, and actually they do it, unfortunately, if it is not allowed, but they do it in many countries, even Arab countries and Muslim countries. They say to you that send one message to certain number, and this message will cost you $1 or $1. After that, there will be one winner in this game, and the winner will get, let's say, a new car, and this new car costs, for example, $50,000, for example, and the message, it costs you only $1 or 1 Libyan dinar. Okay, and the reward will be 50,000, which will be like randomly selected from those who will share in this game. Okay, now I like to ask you, can you compute the expected value of what you get by playing this game? Okay, now what you get in this game, what you get in this game is a random variable X, and this random variable that you will receive, you will lose $1, so it will be -1 times the probability that you lost the game, plus 50,000 if you win the game. So because you either you have one option, either you lost or you win. So it will be 1 minus probability that you lost. Okay, what is the probability that you will win the game? The probability of winning the game is equal to, it depends on the number of people that will participate in this game. So if we assume that there was like 100,000 person participated in this game, so the probability that you will win, it will be 1 divided by 100,000. 100,000. This is the probability that you will win this game. Okay, let me move the slide. So 1 divided by 100,000. If there's 1 million participants in this game, so the probability that you will win, it will be 1 divided by 1 million. Okay, but let us assume that there are only few people that participated in this game, Okay, so in this case, the average that you will get, this is the average that you will get. Okay, so the expected value that you will get, it will be -1 times the probability of loss of the game. It will be 1 minus 1 divided by 100,000. Okay, plus 50,000. Okay, divided by, that is the probability that of that you win, is 100,000. So it is clear that this will be 1, this will be 2. Okay, and this will be -1 times 1 minus 1.00001, which is almost 1. So it will be -1 plus half, and this will be -half. So this is the expected value that you will get by playing this game. So physically, or physical meaning, what this number means, because you share with 1 Libyan dinar, and if you win, you will get 50,000 Libyan dinar. So from where this number comes, why it is the expected value of what you will earn is -half dinar. From where this number comes. Actually, this average, what is the meaning of averaging? Here, the average means that you repeat playing this game like 1 million times. Okay, assume that if you play this game 1 million times. Okay, so out of 1 million times, you will win 10 times. And in 10 times, you will get on the average $50,000 in 10 times. Okay, but in the same time, out of this one like million time that you play, you will lose 90,000 times, which means that you will lose that money as well, because every time that you will play this game, you will put 1 Libyan dinar every time. So if you repeat this game very large number of times, on the average, after playing this game like hundreds of thousands or millions of times, on the average, what you will get is half Libyan dinar, which means that you are loser on the long run. You are loser on the long run. So, and actually, this is the way that those who make this kind of gambling, they are always winner on the long run. On the long run, they are always winner. As far as the game is repeated, they will be honor all the time. They will be the winner all the time, and you will be the loser all the time. Okay, on the average. Of course, there are some people, they play until they got this 50,000, then they stop playing again. Okay, but there is no guarantee when they can get this 50,000. How many times they need to repeat the game until they reach to this number. So now this is the concept of probability and averaging. It plays, or it is very important role in many different applications in business, for example, in risk management, in electrical engineering. If you want to compute what is the average of getting error in probability error on the average, for example, how it will be. What is the average signal to noise ratio, for example? Okay, if we have signal to noise ratio, it was given like SNR, and this SNR, it has certain distribution, for example, Bayesian distribution, and then you would like to compute what is the average signal to noise ratio. For example, we say that if the signal to noise ratio is greater than, let's say 10 dB, then we can get some if the average signal to noise ratio is greater than 10 dB, then we can have like successful communication with certain quality of service. Okay, then we can compute what is the average signal to noise ratio based on the available channel condition, and then we can see that if it is greater than 10 dB or not, and if it is not, how we can improve it. For example, by increasing what is the methods that we can increase the quality of service in wireless communication. One method is, for example, increasing the transmitting power, but this is not a reliable solution, because increasing the transmitting power, it can introduce more interference to the other terminals as well, and the other parameters can, or the other devices, they can also increase their power, and then this will reduce your signal-to-noise ratio. The other method that you can switch from modulation technique to another modulation technique. For example, if you was using 64 QAM, then with this one, we didn't get the required quality of service. We can reduce it, for example, to 16 QAM, because reducing them, it means that we have larger distance between symbols, which means that less probability of error, or maybe also we can go down to for example, to phase shift keying, for example, to phase shift keying, which has the highest performance in terms of probability of error, but at the same time, it has the lowest performance in terms of spectrum efficiency. And as you go up, you can increase the spectrum efficiency, but you lose the reliability of communication. So all these things that we need all the time to have the expectation operator. This expectation operator is very, very important. Okay. Another expectation operator is used, for example, if you have like multiple random variables. You remember when we talk about conditional probability, that we say that probability of x given y, if you remember, we said that it is probability of x and y, okay, divided by probability of y. Okay, and actually the same here we can apply also in expectation as well as in the probability distribution. For example, we say that probability distribution of x and y. This one is called joint probability density function. Remember this, joint probability density function. It can be two elements like this, or it can be any number of elements density function. Okay, so now this joint distribution here, what we put here, we put also x and y in this way. Okay, if x and y are independent, if x and y are independent, then f of x and y equal to f of x times f of y. It is very similar to what we have seen in the probability. And also the same that we can say that distribution of x given y is the same as f of x and y divided by f of y. Okay, so actually what we have seen in the probability and conditional probability, we can extend it directly to the joint probability density function or joint probability mass function. So we can apply them, the same concept, we can apply them again. And also the same way, the expectation of x times y. Here we put also, we can put xy, the same, x and y. Okay, this one equal to, be like focus with me about this. This will be expected value of x times expected value of y if and only if and only f x and y are independent. Okay, if they are not independent, you cannot move them in this way. What is the meaning here? Expected value of x and y is what is the average of two random variables multiplied together. Let me take example. Before I take the example, I will first approve this. Even in this course, I am trying as far as I can, or as far as possible, to avoid derivations. I don't want you to complicate the course by a lot of mathematical derivations. What I want you from this course is the application, to understand the concept first, and then how to apply them by using this like simulation and Monte Carlo simulation. This is the reason that I'm trying to avoid the conventional and the basics of derivations every time. But anyhow, this is not hard to see that if I want to make the expected value of x times y, and x and y are random variables. But assume that in the beginning they are dependent, or in general form. What is the general form of this expectation? This will be, remember, integration, integration, double integration. Why we take double integration? Because we have two random variables. One integration over x and the other integration over y. What we have here, we have x times y. Then what I put here, I put x times y, simply like that. Okay, what is the probability density function of x and y? It will be the joint distribution of x and y, dx, dy, and this will be x and y. Okay, so this is the general formula to find the expectation of x times y. If x and y are independent, then I apply this fact. F of x and y, if they are independent, equal to f of x times f of y. So if I apply this here, so simply it will be, if they are independent, then I will have expected value of y, integration of y, integration over x. It will be x times y times f of x times f of y dx dy. Okay, I can take, because x and y now they are independent, I can take x with x and y with f of y. So simply it will be the integration. I will take this y outside the integration because it is not function in x, it is function in y. And also we take y outside. So it will be the integration of y. Okay, over here it means over y, and here means over x. It means, of course, from minus infinity to infinity, from minus infinity to infinity both. So here the integration over y from minus infinity to infinity, it will be y times f of y dy multiplied by integration over x, x times f of x dx. What is this? This is the expectation of y, and this is the expectation of x, which means that the expectation of x times y, if x and y are independent, will be the expectation of x times expectation of y. Okay, but as you can see during this lectures or these slides, I try all the time to avoid derivations and proofs. Proofs of just take it as I gave it. You need to believe me what I write here on the white screen. If you want to check yourself, of course, it will be even better if you go to the books and read how this was approved. But the proofs here, we try to minimize them as much as I can. I don't want to complicate you with many derivations. The idea is how to use them. Okay, let us see how could we use them. Assume now that you have random process given by this way: x equal to x times y plus e to the power, let's say minus x, okay, plus cosine, okay, x times cosine y, or pi times y. You maybe during your work in your master or PhD thesis, you need to handle this new random variable z, which equals x times y. X is random variable, y is random variable, everyone here is random variable. Okay, x, assume that x is a random variable which is uniform distribution. This is the distribution of x, okay, which is from -1 up to 2. This is fx of x dx from -1 up to 2. Of course, here will be here because the width here is 3, so it will be 1 divided by 3. Okay, and what is y? Assume here that y is exponential distribution given by e minus x. So this is the e minus y. E minus y. This is the distribution of y. Fy of y. It is the distribution of y is e to the power minus y. Now I asked you to find what is the expectation of z. What is the expectation of z? And I told you that x and y, they are independent. X and y, independent. Okay, so the expectation of z, it will be simply like that. It will be the expectation of x times y plus expectation of e minus x plus expectation of x times cosine by times y. Okay, x and y are independent, so this will be expected value of x times expected value of y plus expected value of e minus x plus expected value of x times expected value of cosine by y. Okay, what we need first to calculate what is the expected value of x. Expected value of x can be found from this here. Okay, so actually it is uniform distribution. So we can see that here the width is 3. So that the value, it will be in the middle at 1.2. So it will be 0.5. But anyhow, let us do it in mathematically. So the expected value of x will be the integration over all this area from -1 up to 2. And x times fx of x. Fx of x equal to third, bx divided by 3 dx. And this will be 1/3. The integration of x is x squared divided by 2. The integration limit from -1 up to 2. And this will be 2 squared is 4. 4 minus 1 is 3. So it will be 3. And here will be 3 divided by 2. 3 cancelled 2. 3 cancelled 3. And this will be half. So the expected value of x is equal to half. Okay. And expected value of y, I don't want to use the rules, so I just make the integration. It will be the integration from 0 up to infinity. Okay, and this is the e to the power minus y. So it will be e to the power minus y dy. And this will be the integration of e. Of course, you use divide by -1. So it will be e minus e to the power minus y, integration limit from 0 up to infinity. And now you substitute with infinity, e to the power minus infinity equal to 0. 0 minus 1, e to the power 0 is equal to 1. 0 minus 1 equal to -1. -1, and we have here minus, so the result will be 1. So the average of y equal to 1. What else? Now we compute expected value of x. We computed expected value of y. We need to compute the expected value of e to the power minus x. Okay, so the expected value, maybe it is good that you put the expected value of what? So we put here x, here y, here we expect value over x of what? Of e minus x. Okay, again, this is the integration from, you can see here that from -1 up to 2. This is the integration limit from -1 up to 2. Okay, the value of fx of x equal to 1/3, it is fixed. And then we put here e minus x dx. Okay, so the average of e to the power minus x in this random process, it will be simply, so we have here the integration of minus, so we will have 1 divided by 3, okay, and e minus x, and the integration limit from -1 up to 2, which means that it will be minus third, substitute with 2, so it will be e minus 2 minus e of the power -1, it will be 1. Okay, and this I will use my calculator, because actually I just make this example now, so I didn't prepare it before. So it will be exponent of 1, the exponent of 1, which is, of course, it will be like 2.7 as we know. Okay, minus, it will be e minus 2, e to the power minus 2, okay, and divided by 3. And the result actually will be 0.86. So this is the average of e of the power minus x. Okay, now we compute also this part. So now computed this one, and we have done with this one. E to the power x, we have already computed. What is left? Actually, this one is left. So the expectation of cosine by times pi. So it will be the integration again from 0 up to infinity. Okay, so it will have, we have cosine pi multiplied by y times expected value, the exponent of minus y dy, and the integration from 0 up to infinity. Of course, this integration that we need to solve by part this into two steps if you don't have the table, but you don't need, of course, to solve it yourself. Even I strongly recommend you to practice yourself with these integrations. I strongly recommend you to practice yourself with the integration, with the differentiation, with solving differential equations. Actually, you are coming to be a master student, which means that I know that many of you maybe have been many years from studying these basic things from Math 1 and Math 2 in university, but it is important that to start practicing yourself. Of course, now you can do it by using simple calculator that we have over your mobile phone. Even in my mobile phone, I have simple calculator that they can make this simple calculation and gives you the final result. But still, I recommend you to make it by parts. So the integration is by parts. For example, you take the integration, you keep this one first, and you take the integration for that one. And then when you take the differentiation for the cosine, it becomes sine. And again, you take it second time, it becomes cosine again. Then you can solve this this formula and to find the solution. The time is running, so we don't have time to do it this on now on the line on the white screen, but it is simply done. It takes like 3-4 minutes to do it. So now, after you solve this one, assume that the result of this one, assume that it was, let's say, 0.5, for example, okay? And now you substitute with these values here. You substitute with these values here. We have the expected value of x, we have the expected value of y, we have the expected value of minus x, we have the expected value of x, and we have the expected value of cosine by y. Then we can find the expected value of z. And if I asked you what is the variance of z, so the variance of that sigma z square will be the expected value of z square minus the mean of z that we have computed now square. So, but still, we need now to find the expected value of z square. We said that z equal to, as we have seen here, equal to, this is this, z, okay? So it is x times y, it will be x times y. We said plus e minus x plus x cosine by times y. Now you need to compute the expected value of z square. The expected value of z square, you need to take the square of these values. Okay, some students make a big mistake when they think that the expected value of z square is the same as taking the mean of z square. This is wrong. Okay, so the average of the square values is not the same as the square of the average values. I repeat, the average of the square values is not the same as the square of the average values, because the mu z square is the square of the average values, the expected value of z square. So actually, in electrical engineering, this is the power in the DC part of the signal. This is the power in the DC part of the signal. However, the expected value of z square is the total power in all signal, the total power in all signal, DC and AC. So they are not the same. Okay, so now I remove this. So the expected value of z square equal to what? You take the square of this value. So taking the square, it will be x square, y square, okay, plus e minus 2x, because we take the square for this part, plus the square of this part is x square cosine square by y, plus this one times this one, it will be x times y, e minus x. Okay, and also it will be multiplied again. So it will be multiplied 2 times, so it will be 2. Okay, plus 2x dot y multiplied x cosine by y, so it will be x squared times y cosine by y. Okay, so now I multiplied x dot y times e to the power minus x 2 times, and I multiplied x2 times y times x cosine by y 2 times, and finally I multiply e minus x times x cosine by y, and it will be 2 times because we multiply both directions, so it will be 2e minus x cosine by y. So this will be the we need to take the expectation of all these values. Okay, again we can expand them, so it will be expectation of x squared times expectation of y squared plus expectation of e minus 2x plus expectation of x squared plus times expectation of cosine squared by y plus 2 expectation of xe minus x multiplied expectation of y plus 2 expectation x squared multiplied by expectation of y times cosine by y. Remember, you cannot take out y from cosine by y. It is the same. So now you cannot say that they are uncorrelated. Okay, you need to remember this one. Plus 2 expectation of xe minus x times expectation of cosine by times y. Okay, some of them have been already calculated, like this one, like expected y. Those have been calculated already, but now we need also to calculate the new expectations. So it takes a lot of time, but it is not difficult to compute every expectations here. The easiest thing to solve such a problem, the easiest way to solve this problem is by using Monte Carlo simulation. In Monte Carlo simulation, even if they are dependent on each other, you can very easily generate them by in cosine. If I now just share with you the, sorry that I take more time today, but if I just share MATLAB. Yes. As you can see, I will not repeat the same, but let us take that. Okay, now I will, come on. Yes. I will generate x, and x is uniform distribution. Okay, it is uniform distribution, and maybe it can be for any, maybe uniform one element, and I will generate, let's say, 10,000 of uniform. This uniform is between 0 to 1. This uniform is between 0 to 1. If you made it like 2 plus, now it is from because 0, when run is 0, it's from 2 up to 3. Now this uniform is from 2 up to 3. If you multiply it here by 2, it becomes now, if run is 0, it will be from 2 up to 4. From 2 up to 4. If you want to put here minus 2, I just show you how to generate whatever uniform distribution that you want. Okay, if it is minus 2 plus 2 times random number from 1 to 2000, now this random number, it will be from minus 2 up to 0. From minus 2 up to 0. Okay, if you put this equal to 4, it will be from minus 2 up to 2, because the maximum of the random number is 1. Okay, so 1 times 4 is 4. 4 minus 2 is equal to 2. Okay, if you want from minus 1 to 3, I put here minus 1. Okay, so now if it is from minus 1, the minimum of random is 0. 0 times 4 is 0. So the minimum number of 4 of x will be minus 1. The maximum number of x now, it will be 4 times 1 is 4. 4 minus 1 is equal to 3. So here this random number is from minus 1 up to 3. Okay, if you want in the same example from minus 1 up to 2, simply you put this one. plus 3. So any uniform distribution from any number to any number, you can generate it easily by this form. Okay, this one. You can also generate the exponential distribution. The exponential distribution, there is already function in MATLAB and Octave. It is called, if I remember well, exponential random number. I think it will be in this way. Let me check it. Yes, it will be exponential random number, as you can see. And the first number is lambda. And now if you want to generate like 2 by 1, it will be this one. Okay, so now I want to generate exponential distribution, and this exponential distribution, I want it in the same size, like this one. It will be one row and 10,000 elements. So simply I will say that y equal to exponential random variable, okay, rand. It will be parameter is 1, and the number is 10,000, one row and 10,000 element. Okay, that's it. Now I generate x and y. Okay, now I want to compute z. We saw that in the example that I gave before, that z equal to, come on, yes. So z equal to, we said that x times y, x dot multiplication y, okay, plus exponent minus x of minus x, okay, plus x times cosine by y, x. Remember always to take this dot before the multiplication, because I said this dot means that you multiply element by element, okay? X times cosine by times y. That's it. Now we generate this random process z. Okay, now you want to compute what is the mean of z. The mean of z is the average mean of z. This is the mean. Okay, what is the mean of the squared values? The mean of the squared values is the mean of z square. This gives you, if I saw this mean like z mean square, for example, let us call it this way. So this is the mean of the squared values. What is the variance? The variance equal to the mean of the squared values. The mean of the squared values is mean square minus the mean square, mean of z, and we take the square of the whole mean. So this is the variance. So you can see how easy that you can solve the problem with Monte Carlo simulation. It just in, maybe you need to make the derivation, this derivation that we show now. Maybe if you want to solve it completely with your like hand calculations, it might take like 30 minutes or 40 minutes of integration and differentiation and all these things. And by simulation, it takes less than a few seconds to make it over Monte Carlo simulation. Monte Carlo simulation is a very strong tool. So you might ask, why then need to make it like with calculations? Actually, in order to make the Monte Carlo simulation, yes, I got the mean, I get the variance, I got those values as final values. But I don't have now the probability density function of z. Of course, I can draw it or simplify it by using, for example, histogram. I can see it. But when you make the calculations, if you calculate the probability density function of z, then you can see what is the properties of z. You can see what is the properties of z. where is the most probability Z will be? What is the least probability Z will be? So when we design, for example, optimal receiver in digital communication, we need to know the probability density function in order to optimize our receiver. Okay, so the mathematical calculation is also very important, but the Monte Carlo simulation is also very strong tool that you can use. Okay, now with this Monte Carlo simulation, actually, even if X and Y they are correlated, you can easily simulate it, very easily simulated. However, if the X and Y are correlated in the example that I show now, it is very complicated in order to evaluate them mathematically, because in this case you cannot differentiate from X, or you cannot separate X from Y. You need to take double integration over the joint probability density function between X and Y. And this, of course, can be, like, in some cases can be easy if the joint distribution is tractable and feasible to be solved, but in many other cases can be very, very complicated. In many cases, we don't have even a closed form solution. It is the solution is infeasible, we say, to be done in a closed form. Okay, so I need to stop here. Actually, we have already talked a lot about this, and now we have seen so far the today in the today lecture we saw a few more probability density function, Riley, Raytian, and also we talked a little bit about a chi-square distribution, and also we introduced the topic of mapping between different random variables if we have like deterministic mapping between them, static mapping between them, not differential equation. But if we have static mapping, then we show how to convert from map to map, from probability density function to another probability density function from different variables. After that, we come to the important topic of expectation. We introduce the expectation from its basics. How can we think about expectation? What is the meaning of expectation, which is nothing but averaging. Actually, we take the average, but we extend it over averaging of X to the averaging of X squared, the averaging of variance, the averaging of any general function. And after that, we show also how the concept of joint probability density function, when we have joint probability density function, and what are the conditions to separate them, and also the conditional probability density function, and finally the joint expectation and how to deal with the joint expectation. So after these basics of probability theory, so actually now you are on the track about these main topics. As maybe you have seen from quizzes, the quizzes are not complicated. I will not ask you to make any derivation or to give any proof. Just simply how to apply these concepts that we have taken today. Okay, that's it from today's lecture. And if you have any questions, you can ask. I will stop also the recording now, so to open the questions. Okay.